Alright. We are doing, our senior design is the FSAE Powertrain Optimization Package. My name is Alfred, Salas, and my colleagues are Daniel Oliva and Pedro Cuberos, and our advisor is Dr. Andres Tremonte. What is Formula SAE? Formula SAE is an international collegiate competition hosted by the Society of Automotive Engineers. What this allows is for participating students to apply their engineering skills gained in the classroom to design a formula-style open-wheeled race car. So pretty much we start from scratch, from CAD all the way to a finished product. We do all the manufacturing as well as design for practically all of the components. So for FIU to design a SAE vehicle efficiently to have an overall well performance, we break the team down into 7 categories. We have powertrain, chassis, drivetrain, aerodynamics, electrical electronics, business marketing and e-board, and ergonomics. As you've seen in the previous teams that went before us, these categories break down even into more subcategories. For example, the chassis includes steering, your suspension components. Powertrain is our intake manifold and engine management. And another thing that should be noted is that due to the infancy of the FIU SAE organization, we typically only have about 20 active members a season. So if you do the math, that pretty much breaks into 3 members per category. So this is our current design for the 2015 SAE powertrain. What our new design is going to include is incorporate an intake manifold plenum. We're also going to relocate the intake away from the exhaust. This way the thermal radiation effects do not affect the air density. This way we have a denser charge for higher performance and better air-fuel atomization. We're also going to be introducing thermal coatings to the intake and exhaust system. Luckily, we've been able to get a sponsor from Engine Armor who's willing to pretty much thermal coat practically every single component on the vehicle, down to pistons, crankshaft, rotors, brake pads. But for the scope of this project, we're only going to be focusing on the intake manifold and the exhaust and the effects and the performance increase we're going to gain off of that. If we have any extra time, we're also going to be transferring the thermal coatings to the radiator. It should also be noted that we're going to be switching the material. We're looking into carbon fiber as well as SLA 3D printed intake manifold. We've also been able to allocate another sponsor from Realize Incorporated who's willing to 3D print the whole entire intake manifold with a integrated injector housing for 75% off of the regular cost. We're also going to be designing a tuned header to match the intake manifold, and one of the overall goals for this project is reduce the overall weight as well as increase the performance. So pretty much to get a baseline of how to design the intake manifold, one of the things you need to calculate is the intake airflow at a given RPM. So pretty much how to do this, you use the calculation here, which is engine size. We use cubic inch diameter, which is given. I should also mention that the engine that we're going to be using is a 2009 Yamaha YSZ 450R, which is a 4-stroke, single-cylinder, dual overhead cam engine. So the cubic inch diameter for this motor is 27.4. The calculation goes further by multiplying that by the RPM as well as dividing by a conversion factor. The Yamaha YSZ 450R is a race engine delivered from Yamaha. So one of the main influences that affect the intake airflow is the volumetric efficiency. Since this is a naturally aspirated engine, the volumetric efficiency for a high-performance engine is roughly 90%. So that would be 0.9 in our calculation. It should also be noted that for supercharged and turbocharged engines, since you're applying boost, which you're pretty much forcing air into the intake and as well as the cylinders, the volumetric efficiency exceeds 100%. Next. So to give you an idea, we did our CFM versus RPM graph. We started from 2,000 RPM all the way to 11,000 RPM. We also broke it down from 90% volumetric efficiency, 85 and 80. This intake's going to be designed for pretty much a running RPM around 10,000 RPM. With 10,000 RPM at a 90% volumetric efficiency, that gives us roughly 71 CFM. So for an internal combustion engine, you have 4 strokes. You have intake, compression, power, and exhaust. During the intake stroke, that is the only time that the intake valve is actually open. Therefore, it's only open for 27 or 25% of the internal combustion cycle. When the intake valve is open, the piston is moving down in the cylinder. What this creates is the vacuum. With this pressure differential from the atmospheric pressure and the vacuum created inside of the cylinder, that's what creates your intake air velocity profile. One of the biggest concerns that we have with the current intake manifold is that there's no intake plenum. The reason that we incorporate an intake plenum on a single cylinder engine is that when the intake valve is closed for the remaining 3 cycles, compression, power, and exhaust, the incoming air velocity profile bounces off of the intake valve. What this causes is a compression wave. What that compression wave does is distorts and pretty much interrupts the incoming airflow. So what we're doing with the intake plenum is that we're pretty much going to incorporate a plenum large enough for the CC of the engine as well as the CFM required, but also most importantly is to mitigate or reduce the effects of the compression waves so it doesn't damage the incoming air velocity profile.
So building off of what my colleague Alfred has spoken about, me and Alfred have both worked in the automotive industry as interns for General Motors, and we plan on replicating the design process that the automotive industry uses, which is going from a component level towards a system level. So therefore, for a component level, our goal is to design multiple iterations with using CAD software, in this case SolidWorks. And once we split up the amount of iterations that we each are about to do, we then plan to go into analysis and Anson's fluid. From there, we will determine at what velocity our car is going. We'll determine that we will use that velocity for the incoming air charge, also atmospheric pressure since we're not naturally aspirated. And then once we get all the results files from every iteration that we do in a 3D analysis, we will then use a Mode Frontier optimization software. This software will allow us to gather all the results from every iteration that we did and basically determine if we're looking for the least amount of pressure differential from the inlet to the outlet or the most laminar flow. The software will allow us to basically give us the best 5 iterations depending on what we're looking for. And then once we get that, we will move into the system and at the system level by using a Ricardo Wave engine simulation software. We have also gathered a sponsorship from there where they gave us 5 licenses for us to use. So in that software, we can build an entire model of our engine and give it the different parameters such as the bore stroke, the valve diameter even, and we can input the ANSYS results right into the Ricardo Wave model, so it can take that into account and it can give us the best performing iterations in terms of horsepower and torque, not just pressure difference or most laminar flow. Then once we do that for the best 3 iterations, we will narrow down to 5. We're gonna, 3, I'm sorry. Once we go from 5 to 3, then we'll manufacturing the best 3, either out of carbon fiber or a 3D printed material. Myself, we have had experience in manufacturing carbon fiber in the past, so we know how we would be able to do that efficiently. And then once we manufacture all 3, we'll go to a chassis dyno and install each intake on the car, measure the horsepower and torque curves relative to RPM, and decide on the final best iteration.
The project is divided in 3 main stages. Each stage is designed to last 2 months, and we're currently standing at the end of the first stage. We're using a software called SmartDraw, which is not only allowing us to assign tasks to each one of the members of the team, but to also keep track of the due dates and the progress of each one of the stages. As I said before, we're almost about to complete the first stage. From the 5 initial tasks of the first stage, 2 of them were already fulfilled. These ones are the complete CAD model of the current vehicle and the space restriction analysis of the rear end of the vehicle. We're already starting to work on the second stage by generating the different iterations of the CAD models of the powertrain prototype.
Finally, keeping in mind with the global design goals, Formula SAE is a competition that features 125 schools, not only from the U.S. but from around the globe. With that in mind, the rules set for Formula SAE that we must follow correlate with global standards from the automotive industry. So there are things that you would see not only in the US, but when you're competing in a global market. The nature of our project is to optimize the intake and more specifically optimize the volumetric efficiency. By doing this, we are also reducing the amount of emissions that that our car is sending out, and this is a current problem in the automotive industry that's very heavily stressed, and a lot of companies are struggling to be able to keep up with governmental standards. So the methods that we learned in this project will be able to apply in the automotive industry once we move forward with that. And finally, by increasing the performance and the volumetric efficiency, not only are we increasing performance, but we're also benefiting the planet and the atmosphere. Any questions?
I have a couple of questions for you. First one is a comment regarding your presentations. There are certain slides where you have text that it's very, very small, like when you showed your project management photo. So next time, you can do a snapshot of it, but just make it bigger. Second is you mentioned fluid analysis, you mentioned your solid work modeling, but being a one-cylinder engine, you're going to have a lot of vibrations coming out of your engine, so you should consider both static and vibratory stresses in ANSYS. And another comment regarding your cost, you mentioned that you're manufacturing for 75% of what it discount.
Yeah.
But what's your current budget? Is there a specific estimate that you've done? Do you have the funds for it?
Pretty much, we've also, besides the regular sponsorships that we've mentioned, we've also gotten a $500 donation. But luckily, we also have another company. So let's say we were to go the carbon fiber route. We have a company that pretty much donates us carbon fiber. And luckily, since Danny he was the chief engineer for the aerodynamic body, so he has experience making a whole entire carbon fiber. So if the cost was too much, we could go that route. However, since we don't have a final intake design yet, we haven't sent out the CAD file to the 3D printing company, so that's why we haven't gotten a solid answer of what it's in exactly cost for our specific design.
So my suggestion to you is ask the company for any sort of component that they've done similar to this. It doesn't have to be the exact. That way you have at least an estimate on what price you have to.
No, we can definitely do that because the company that actually sponsors us, they do multiple other SAE formula teams, so we could just simply get a price quote of what it would be for a similar single-cylinder intake manifold, 3D printed.
Now, you guys going to competition?
Yes.
Are we going?
Yes.
Yes.
Now, which team is going to be responsible for writing the cost analysis report?
We have a whole team dedicated to that actually. So currently our Vice President, Juan Trujillo, is currently in charge of doing the cost analysis and also the business strategy. And he has a team of new members, which he's they're new on the team, and he's delegating that work to them so that they can get a little bit more exposure to that side. And we feed him the information from our team and say, this is what this material cost us, this is how much time they spent, this is how much donated material we got, and how much that material is worth. And he inputs that into his whole cost analysis for the whole team.
How big is the FIUSE team?
It's roughly about 20.
About 20 strong members.
That's good. I remember when it was like only 5 or 6.
Yeah, we've grown in the last few years.
Okay, that's good.
More questions?
Just a comment. Very well done having your trackable milestones. It's the first one I've seen today, and it'll help you out a lot being on time.
Thank you.
Thank you.
Thank you.
And we're down to our last presentation, 2023, also on Formula SAE